Welcome to MOOC Interactomics course. Today we have a guest with us, Professor Cynthia Go. She is a professor in Department of Chemistry at the University of Toronto. She is also Director of Optical Sciences in University of Toronto. In our previous lectures, we have discussed about various label-free methods, including surface plasmon resonance based optical biosensors to measure the biomolecular interactions, especially the protein-protein interactions. Today with Dr. Cynthia Go, we will discuss about diffraction-based biosensors, which her lab is actively working on. During this discussion, she will also demonstrate some examples as to how these diffraction-based biosensors can be used for measurement of molecular interactions and their applications in different type of diagnosis and point of care diagnostics. I would like to welcome Professor Cynthia Go, and we will talk more on the how to measure protein interactions. Welcome, Cynthia.
Thank you. It's a pleasure to be here. As you know, biosensing is about the measurement of interactions between two biomolecules. And I'll be discussing an unusual approach, which actually is surprising that it hasn't been used before, but it was invented in my lab, which is to examine the interaction between two sets of molecules using the principles of diffraction. So let me just take you back to what you may remember from either your basic physics course, or perhaps you may have met diffraction in the context of X-ray diffraction on crystals. If you look at the right-hand side there, I have two slits. If you've been watching waves of water passing through two slits, you see that there's diffraction, these little wavelets that are formed that results in an interference pattern that has light and dark spots. So in the middle part of this slide, we see a beam of light passing through a grating, a diffraction grating, and it shows the main beam and a lot of little beams that's generated. And the pattern of this diffraction image, the image of the diffraction, depends on the pattern of the grating. So let me show how we can use diffraction, the principles of diffraction, to actually measure the interaction between molecules. So let me take a piece of glass slide here and put a coating, just one molecular layer thick of coating that is in a pattern. So this is a grating, lines made up of biomolecules that are spaced approximately a micron and a half apart, such that when light is shined through that grating, which is very faint, there's going to be a little bit of diffraction, not much. In fact, you could barely see it in this cartoon drawing. However, if binding were to take place, so that this molecule now has a complementary partner binding to it, so you can imagine this yellow one is protein 1, the green one is protein 2. What you see is that the grating becomes more pronounced, and so when light shines through that grating, you're going to get a much brighter spot. So again, let's just do this in a different representation. I'll take you to a different slide where...
So Cynthia, it means you are actually measuring how much material is there, and to begin with, if we have small material, 1 nanometer size, and then if we are adding more material to it, then the change in the diffraction that is being measured. Right?
That is correct. So effectively, we have a surface first like a piece of glass where light will go through, and when there's just imagine writing with your pencil lines on that piece of glass. If you shine light, you're going to get a diffraction. Except the lines that we're writing is one molecule thick, which is one protein layer thick.
Right.
And so the diffraction is very faint. So let me illustrate that in this little cartoon. So the sensor surface is a piece of glass. It has lines, as you can see in this inset. And when I shine light through it, there's going to be a very faint signal. Now, supposing I introduce molecules that bind right on this line, the signal gets darker, and it's represented in the right-hand side here by the intensity of light. So effectively, if I have a detector in one location, you can see that the signal increases with time as binding takes place. Now, if I were to introduce a second molecule that binds to that first one, again, the signal gets darker, so my detector then has an intensity increase with time.
So good thing is multiplexing is possible in that way.
We can talk about multiplexing in a different one. This one is basically, this is one molecule binding to another molecule. You can also bind a second one. Sure. So you can imagine an antigen and an antibody and a secondary antibody. You can also play games. If you're into trying to measure relative strengths of interaction, you can imagine trying to imagine whether you can displace this antibody with another thing. So here's something coming in, another molecule, and if the binding is stronger, it may actually detach the previous one, and that will be indicated by a change in signal, in this case, a decrease in signal.
So I think very similar to what we had taught in the previous class on the surface plasmon resonance methods. I think same way we have the baseline here, and we are measuring the time versus intensity on X and Y axis.
That's
and
right.
Then we will have an on rate, we will have an off rate.
That's
depending
right.
on the interaction, how it is strong or weak, one can actually compute the values for measuring the on rate, off rate, and the kinetics of it.
That's right. So it's very similar to surface plasmon, and in fact, a lot of the principles are similar in that it depends on the index of refraction difference. Right. The main difference here is that in surface plasmon, you only are looking at the main beam. In this case, because we are putting things in a pattern, then you're going to have a diffracted beam, and we're looking specifically at the diffracted beam. And there are advantages of doing that. Mm-hmm. So why would we actually want to measure this way instead of just directly through surface plasmon? Well, you can actually imagine in one area. If you're doing surface plasmon, you can only put one molecule in that area. That's correct?
Right. I think also like now there are some newer methods where people are trying to have 4-plex or at least
that's
6.
right. Now you have different areas and you can put things down in different areas. Right. So in the case of diffraction, you note that there is a one-to-one correspondence between what your grating look like and what your diffraction image looks like. Right. So even just if I have a grating facing one way versus another way, I will have this grating will have dots in this direction, this grating will have dots in this direction. And therefore you can identify whether molecule A is binding to this one versus this one.
Sure.
So you can multiplex very easily, and that's one advantage. From the technical perspective, we can actually choose that kind of pattern to enhance the signal and therefore create a better sensor in many cases. But from if you were trying to look into the diagnostic area in the future, one advantage of getting diffraction pattern is that if molecule B is not binding but just drops somewhere accidentally, we call that non-specific binding. Right. In surface plasmon, you will measure that because it attaches to the surface. Right. In a diffraction experiment, if you don't drop in a linear or a grating pattern, then you won't get a signal.
So it means like you are able to increase the specificity here and much more controlled manner as compared to what one can do in SPR and other methods.
That's right. You can reduce what's called a false positive, where you get a signal that is not really meant to be a signal.
Sure. I think that's a big advantage because when you are talking about diagnostics and you are looking at the very specific signal, I think giving a false signal can actually be very different.
For diagnostics, that's very important. But even for experiments in your lab, you of course do not want to have big error bars because some proteins just like falling out of your solution.
Exactly.
Okay, so let me show you just implementation-wise how simple this can be. As I said, this technique was invented in my lab, and here's the example of substrate where we've patterned the biomolecules, this protein on the piece of glass, and it's a submonolayer coverage. It's very small, a very sparse amount of protein in there, and it's imperfect. As you can see, it's not even at all. Right. But it doesn't matter because diffraction is defect tolerant.
What do you mean by defect tolerant? Because if there is some defect, are we going to have different type of diffraction pattern, or that can be compensated because of the nature of diffraction?
Yeah. Well, the nature of light is such that it will pick out the repeats that is of the order of its wavelength or higher. And so if you look at this picture, this is an atomic force microscope image. So the little dots in there are proteins. And you can see that there's areas where there's sparse coverage and areas where there's more of them, and you can see a lot of clumps.
Right.
But as far as light is concerned, it doesn't matter because these clumps are non-repeating. And if
Okay.
they're not periodic, it doesn't show up as a signal. And so it ignores all this. You see, this is probably a protein that just, or maybe this is a piece of junk, and it ignores that completely.
Okay, so I think some error can be tolerated in that way. The defects.
That's right. And so from the point of view of building a device and building an instrument, it doesn't have to cost much because you don't have to make things perfect.
Yes.
Making things perfect is very expensive.
Yeah, but still at the end we can get the perfect signal. I think that's what matters.
That's right. So again, let me just show you in the different region. We have here the grating made up of individual protein molecules. And then binding takes place on it, more binding takes place. And what happens is, here's the surface before binding. You can see that the coverage is not very strong. After binding, the coverage is strong, and you get a much bigger signal, intensity of signal. So you can quantify that. And here's an implementation of how simple it can be in our lab. Really, it has three components. The light source, which is, in this case, a laser pointer. It's a 3 milliwatt red laser. And the detector here is, this is a CMOS detector, but it could be a webcam. It could be what's called a photodiode, which is a very inexpensive piece. And here is the sample cell, and let me enhance that.
So it seems you have a prototype earlier to begin with.
Well, this is how we built it in the lab, right?
Sure.
Because, you take pieces and put them together.
Right.
This is where the actual interaction takes place. And let me just do that schematically. So at the bottom here are two pieces of glass slide separated by a double-sided tape. That makes a channel that's about 50 microns. That's the thickness of the tape. And on one of the glass slides, you put down the pattern of the proteins, and it's out here so that you can then flow your analyte, your medium with the analyte in between.
Right.
And on the other side, we put in a prism. The prism helps to guide the light so that we're under what's called total internal reflection. So the light doesn't go all the way through, it just skims the surface and actually detects the binding on this upper substrate. So it's a very simple.
So when you have a prism, then you have the matching fluid for refractive index correction. Then you got the slides which contain the protein.
That's right.
And then with the light beam, then you are initiating
That's
the
right.
diffraction.
Yeah, and with this simple assembly, you can actually measure down to nanograms per milliliter, label-free. So these other components in this setup are simply mirrors to make it a little bit more compact.
Okay. And that's a very neat concept, and I think then one can actually build various applications on it.
That's right. So in our, as I said, in our first implementation, it's a diode laser, a laser pointer, and a webcam. And these are actually pictures captured from the webcam as you actually monitor the change in intensity on one spot of the diffraction image upon addition of analytes. So after a few minutes, it gets darker, and then it gets darker even there. Okay. The role of the prism is to make sure that the light beam doesn't actually get scattered by whatever is in solution. So here's a picture of what the diffraction spot would be if there were no prism, if it's not under total internal reflection. With total internal reflection, we get it a lot cleaner, and that means you can actually use a fluid like blood or something that's equivalently murky.
So many times I think if the intention is to look for some biomarker or some sort of diagnostics, so measuring blood or serum becomes very important, right?
Mm-hmm.
And actually measuring that is very challenging because of the issues it had. And that's where I think correction for this type of scattering.
Yes. But even in doing your experiments, like if you're using cell lysate, for example, then cell lysate has a lot of particles and it will actually scatter light.
Definitely. So we have a lot of complex samples. It's not always the clean purified protein, right? Which one has to look for the direct application.
So in this case, you don't have to purify your sample before you actually do the experiment.
That's right.
Yeah. So, if you have, we said before about multiple analytes. So in this case, you can have protein 1 in one direction and protein 2 as the other grating, and you end up with 2 grating patterns. And here's a webcam image of what it would look like. So this spot here will be due to protein 1, whereas this spot perpendicular, the spots perpendicular will be due to protein 2.
Right.
And so if you introduce your medium, if this spot lights up, you know there's binding to protein 1. If this spot lights up, there's binding due to protein 2.
Sure.
So you can examine multiple analytes that way. So to show specificity, here's our example now. Now we have the names for the analytes. This is a mouse IgG on one analyte. The other one is a rabbit IgG. So when we introduce anti-mouse IgG, you can see the increase in signal in one of the spots, but not in the other spot, the red versus the blue. And then at this point, we introduce anti-rabbit IgG, in which case one of the spots, the second spot increased, but the first one just remained constant.
So actually one need to show the specificity of the assay, and I think to test it out, you have probably mobilized different type of proteins,
That's
including one from rabbit, one from mouse.
Yes.
And now when you're looking at how specific the signals are, then only anti-mouse is binding on the feature where we have the mouse IgG.
That's correct.
And the one where we have the anti-rabbit IgG, it's only binding with the
That's right.
rabbit IgG.
That's right. And so, yes, and this is showing it with 2. So now you can actually imagine generalizing it with more,
That's right.
and it only is a question of how many you want to pattern into that little substrate that
Another
you have.
important point here is that you are able to measure the signal simultaneously for all the
That's
features. So then actually you can compare those visibly while the experiments are going on. So it just gives a little bit more room for even errors, right? One can actually correct for the errors. One can try to change the concentration of antibodies or different analytes, and one can have different room. I think that's one of the other major advantage of having the label-free systems, where user can have the visible feel of the experiment,
Right.
how it's progressing.
Yeah. So label-free detection is how you would actually do it best if you're trying to measure kinetics, for example,
Right.
right? Because you have the actual signal not adulterated by a secondary reaction. But in this case, having multiple analytes is actually very good in building in controls, because you can imagine one of your spot is always a control. And in fact, we do that routinely in my lab when we're doing measurement.
I think controls are very important. I think that's where it's good to have these features.
So just to summarize the features and advantages, we actually talk about being able to detect more than one at a time simultaneously. Of course, the question is, why would you want that, and how many is a good number? And that really depends on what project you're engaged in.
But usually, based on your experience in the field, for diagnostic purpose, what do you feel like what will be a good number in terms of how many one need to measure simultaneously?
Well, I think it's a question of cost now, right? The more things you put down, the more expensive it becomes. So in any disease, you're identifying how many markers do you want, or if you want multiple diseases, how many of them are likely to occur at the same time. So I'd say it should be less than 10, because chances are you're not going to be sick with more than 10
That's
different
right.
things. And in a complex illness like cardiovascular diseases, probably there's 4 or 5 relevant markers that one would like to detect.
Right. Yes, one has to actually take a call, in terms of what they are actually trying to measure. And I think having as a good marker is always good, but having too many is also not good, because controlling them and actually keeping them functional for a long time, again, all the
That's
cost for the measurement and everything comes
That's
in the
right.
picture.
Yeah. So I'd say somewhere between 4 and a dozen is probably what's
That's the
a
best
typical number.
Sure.
Yeah. So the approach is also quantitative, because, of course, the intensity of the signal is proportional to the amount of the material that's gone down. And it's, of course, you have to run calibration curves to keep that standards going. As we mentioned earlier, that there's little false positives, because if things don't fall down on a grating, then it's just not going to be measured. And that the information is real-time. Again, that's characteristic of all label-free techniques. It's a real-time measurement of the actual interaction.
Right.
And therefore, you can extract from it kinetic information, binding information. In our case, though, the sample volume that's needed is very small. It's really, all depends on how good that little sample cell is. As I said, using double-sided tape, we can get it down to 20 microliters. And that's like a small droplet.
Right, I think that's very important, right? Because if you're talking about clinical sample and measuring the things in the clinical settings, I think it's very important how low we can go.
That's right. But even in your experiments in the lab,
Yeah,
right? Because proteins are very expensive.
Yes.
So if you have the smaller that is, the more experiments you can do for cheap.
Definitely. So it's always better to do in the small volume, what is possible.
Yeah. Now, the sensitivity, people ask me, how sensitive can this get? Well, if you notice that it's all about measuring that grating. So the more pronounced that grating, the bigger your signal. And therefore, if you want to work with low concentration, it depends on how big your molecules are. The bigger the molecules, the better your signal is going to be.
Right.
But also, the stronger the binding, the better your signal is going to be at low concentrations.
Right.
So there's no direct answer to that, but in some sense it would be comparable to SPR because it's based on a similar principle, which is there's an index of refraction change at that interface. It's label free right now, but actually if you want to get better sensitivity, you can also add labels. So you can actually start with protein 1 or an antigen, you put in an antibody, and that's your binding. If that signal is too weak, you could put in a secondary to identify your antibody.
That's, I think, very important because if you're not able to detect the signal at very, very low level, then obviously you have to have some mechanism to bring the signal up.
That's right. You can amplify. Or perhaps the other way of doing it too is that the signal may be low and you need an instrument, you need a good photodiode to do that, but then you want to sometimes amplify it so that it's now visible to your eye, and then what you can do is you can add your secondary.
Right. Thank you very much.
And thank you.
Thank you very much, Cynthia. This was very insightful. So we learned from this lecture that how one can build devices from the physics principle and use it for various biological applications. We learned the principle of diffractive optics technology and some of the features and advantages of this approach. We will continue our learning with Cynthia on diffraction-based biosensors and discuss some of the examples of molecular interaction in our next lecture. Thank you very much.